course is devoted to asymptotic methods in physics applications. Motivated by this, we'll start our first lecture with a discussion of some simple examples, which are related to asymptotic approximations. So first we'll show that some integrals can't be taken exactly, and we'll just discuss how the series of step-by-step approximation can be constructed. And we'll notice that most of the series which one encounters this way are in fact not convergent, they're divergent, and one needs to have special understanding to make some reasonable results from them. We'll show how the series can be constructed by simple integration by part technique. And then we'll switch to more advanced methods, like Laplace method or the methods of stationary phase. Probably you have encountered this method before, but today we'll address them from more formal perspective. We'll actually show how the full series can be reconstructed from simple, like Laplace type technique. We'll also consider the case of so-called super and hyper asymptotics, where you just try to get the least possible error from your asymptotic series. That's it, I think. So let's start.
When we solve problems in physics or engineering applications, say differential equations or whatever, we encounter integrals that can't be taken exactly. But any reasonable problem usually has a large parameter, so the approximation scheme becomes very important. Thus, it's the command of approximation methods that becomes a crucial skill. That's why we start our course with an integral. Let's consider the classical example, the following parametric integral. The integral in question can't be computed exactly. The best we can hope for is to find a reasonable estimate for it at some values of parameter lambda. One can clearly see the decaying exponential in the denominator of the integrand. It facilitates the convergence of the integral. If the exponential decrement lambda is large enough, we expect the integral to accumulate its value at not very large x. Essentially, the presence of the exponential with a large lambda guarantees the good convergence of the integral. For clarity, I plot an exponential function. We could say that the crucial x segment for the integral is from 0 to, say, 1 over lambda. Therefore, the estimate of the integral at large lambda doesn't seem to be that difficult and looks like a reasonable problem. This way, we state our first task. We'd like to compute our parametric integral at large values of parameter lambda. So how do we do this? Since we understand that only small x are important for the integral, the first step that seems reasonable is the Taylor expansion of the denominator, 1 over x plus 1, in powers of x. We plug the expansion into the initial integral, and as a result, the integral can be represented as an infinite sum of simpler integrals. We are quite lucky. Each of the incoming integrals can be taken exactly. There is a special technique in math for this. It's called the differentiation with respect to parameter. Let's consider the first integral in the chain. Let's call it I0. Here, pay attention. I explicitly wrote its dependence on the parameter lambda. The only place where lambda enters the integral is the exponential function. The limits of the integration don't depend on lambda. Now, let's compute the derivative of I0 over lambda. We need to differentiate the integral. Since the limits don't depend on lambda, the differentiation can be pushed through the integral sign, so it acts on the integrand only. And now comes the interesting point. The differentiation of the exponential with respect to lambda brings additional minus x in the integrand. Therefore, the first integral in the sum is turned into the second one with simple differentiation with respect to parameter. So if we denote the second one by I1, then I1 is simply the minus derivative over lambda of I0. Now let's try to do the same trick twice. We differentiate I0 with respect to lambda 2 times. Again, the derivative is pushed through the integral sign and acts on the exponential only. This time it brings two minus x factors into the integrand. This way, we obtain the third integral in our series. So I2 is equal to the second derivative of I0 with respect to lambda. Now I hope you see where I'm aiming at. Let's turn the page. So, this is our series of integrals. You notice the alternating sign. So, let's write down the general expression for the nth term. It is as follows, with -1 to n responsible for the flipping sign. And here is what we have discovered. If we denote the integrals entering this series as I0, I1, I2, I3, and finally In, then there exists the following relation. I1 of lambda is a minus derivative over lambda of I0. I2 of lambda is the second derivative of I0 times -1 squared. In the same manner, the third derivative of I0 of lambda, being pushed through the integral sign, brings -x cubed into the integrand. So we obtain I3 times -1 cubed. Now the pattern is crystal clear. The nth derivative of I0 simply yields In of lambda up to sign factor. So multiplying both parts by -1 to n, we get a very convenient expression for our In integral. The idea is, of course, that instead of taking each integral separately, we substituted integration procedure with the differentiation with respect to parameter of the simplest integral in the series, I0. But we know the answer for I0. It's an elementary integral with elementary antiderivative, so it's simply 1 over lambda. Substituting 1 over lambda instead of I0, we may find out all the rest of the integrals by simple differentiation of 1 over lambda. So here is the answer for the nth integral in our series. It's just the nth derivative of 1 over lambda. Now we can figure out the derivative yourself. The way I usually do it, I just make the first 3 differentiations and then guess the pattern. So the first derivative is -1 over lambda squared. The second one is 2 over lambda cubed. The third one is -2 times 3 over lambda to the 4th power. Now again, the pattern is kind of looming. We notice the alternating sign. The factorial factor is accumulating in the denominator. And this is our guess for the general nth derivative. Next, we plug it into the expression for the integral In and get the final answer. By the way, as a bonus we also obtain the suitable integral representation for the factorial. If we plug in lambda is equal to 1, we see that lambda term in the denominator disappears. So the factorial is now given by the following integral. So, this was the short but detailed excursus into the idea of differentiation with respect to parameter technique. I highly recommend you to practice it. Sometimes it gets pretty powerful. For example, Richard Feynman, in his book on path integrals in quantum mechanics, gives an example of the integral which can't be computed with the help of complex analysis. The only way to evaluate it is to use the differentiation with respect to parameter technique. Here is the integral, so give it a try. I'll show you how to work it out at the end of the lecture. But now back to our initial monster integral. So this is the integral and its expansion. By now we have computed all the constituent integrals and can rewrite it as the following sum. So how do we sum up this series? Well, before discussing this, let's try to understand how this series works. By now, you've probably already understood that this is an approximation series. Each term represents the correction to the sum. You see that at sufficiently large lambda, the second term is much smaller than the first. The third one is much smaller than the second one, and so on. It's a sort of realization of the methods of consecutive approximations. So let's actually plot different approximations. We take reasonably large lambda from 1 to 5 This is an exact function I of lambda, computed numerically with Wolfram Mathematica package. You can look up the Mathematica code in the supplementary materials to this lecture. And this is the first approximation, which is the first term in our series, I node of lambda. It's simply 1 over lambda. We see that the error being large at small lambda gradually diminishes with the growing lambda. Now let's plot the next order approximation. It's the sum of two terms in our series, 1 over lambda minus 1 over lambda squared. We see that it gives even bigger discrepancy for lambda of the order of 1, but it performs better for large lambda. Finally, the third order approximation, which is the sum of three first terms. And you can see that at small lambda it's simply no good, but at lambda of the order of 5, this approximation works the best. So think of what is happening. The more terms we take into account, the worse the approximation works at small lambda, and the better it works for ever larger lambda. So the larger the lambda, the better the senior order approximation behaves. So it kind of reminds the Taylor series of expansions. Indeed, Taylor series of some function f of x gives ever better approximation at diminishing x. Here the role of x is played by 1 over lambda. So the larger the lambda, the smaller the x, and the better the approximation is. But there is some strange peculiarity. We know that even for large x, the Taylor series works better and better if we sum up more and more terms. Here, large x corresponds to small lambda, but the tendency is the opposite. And more surprise is coming. Let's collect, say, 11 terms and plot the 10th order approximation. And this is terrible. The function is completely off its target everywhere. So let me show you how the error gradually changes when we add higher and higher order terms into our series. Let's concentrate on the large limit, lambda is equal to 5. So as you see, the error diminishes until we reach n is equal to 5 order term, where the error attains its minimal value. And then the error starts to grow again until the function goes completely off. This is highly unusual. If we add several terms, we improve the accuracy. But once we take too many terms, the series stops converging to the initial function. This is entirely different from Taylor series expansion. As you remember, when we add higher and higher terms in Taylor series, it gets more and more accurate. So this is definitely not a Taylor series in 1 over lambda. So what is happening? Why does the function start deviating from the lawful value? And the answer is the series diverges at any finite lambda. We can already see this right on this page. But let's turn to the next slide so I can explain this crucial point in more detail. Before we do so, however, let me draw your attention to the fact that the initial integral is convergent, yet the series representing it diverges.